This slidecast will examine the implementation of a vector class. We are going to look at a simplified implementation of the vector class, and we will encapsulate it in the namespace KW, which is a namespace for our textbook authors. And this is where we'll show some of our own implementations of some of the standard types in the standard template library. Now notice we have class vector. It's a template class. And this KW : vector will distinguish our implementation from the implementation in the standard library. Here are some private data fields. Now the physical size of the array is going to be indicated by current capacity, and it's type size t because it's a non-negative number. The number of data items that are actually stored at any given time will be num items, also of size _t. We will use a C++ array internally to contain the actual data of our vector class. And the elements between num items and current capacity are what's available. So that the gray area here represents space to add new items. The blue area would be the space that's occupied by data. And that distinguishes the meaning of num items from current capacity. So stop and study that definition until it's clear for you before you continue on. Now, because this is a template class, all of the code must be in the header or in a file included by the header. And the default constructor initializes the values of num items and current capacity, and it allocates the initial data array. So here's our constructor for our vector class, and here's the initialization list. And the data is dynamically allocated using the new operator. And our capacity is our default initial capacity, and we start with 0 items in our vector. The swap function exchanges the values of this vector object with another vector object, and it uses the standard template function to swap the values. So here is the swap function. It's declared in our vector class in the KW namespace. It takes a vector, a reference to a vector as a parameter. The parameter name is other, and we're going to swap the items in this other vector with this vector, the vector on which we invoke the swap operation. And because the vector class is defined in the standard template library, we're going to make use of that existing swap function to do our swap. So the standard template swap is going to swap other.num items with num items. And then we're going to swap current capacity with the other current capacity, and then we're going to swap the data. There are two forms of the subscripting operator are provided. One returns a modifiable reference to an item in the vector, and the other returns a non-modifiable reference. So here are the two declarations, and the second one is const. And there's two occurrences of the keyword const here. This const we've seen before. That means the function is const. It doesn't make any change to the object. And this const applies to the return type. So this reference to an item is a const. That means it cannot be updated. And the second declaration is the one that is appropriate for the expressions on the right-hand side of an assignment operation. So the compiler invokes this const version whenever we're on the right-hand side of an assignment operation, and it invokes the non-const version when the subscript operator is applied on the left-hand side of an assignment statement. So the body of the code for both forms of the function is identical. We verify that the index is legal, and then we return the data at that index. Now in our implementation, we validate the value of the index. Now the standard vector subscripting operator does not do this. So our implementation is equivalent to the standard vector function at. So the standard library, the at, does bounds checking. The subscripting operator does not. Now the inventor of C++, in his book, he suggests that a programmer could define their own vector class that overcomes this limitation as follows. So here we're overloading this operator and have it simply call the at function. So here we're going to overload the operator, and because we'll call at, that means bounds checking will be done. The new template class myVector is defined as an extension of the standard vector class. You can see here, and the subscripting operator in the standard class is overridden with ones that apply function at. The pushback function appends an item to the end of a vector. So if num items is less than the current capacity, then there's space to add the new item, represented by this dark blue. So we'll insert an item that's pointed to by num items, and then we increment num items to point to the next available space. If num items is already equal to current capacity, we must allocate a new array to hold the data and copy the old array to this new array. The member function reserve does this, and we'll see that shortly. Here's the implementation of pushback. It takes a const reference to a value. It makes sure that there's enough space. If it's full, then we'll call reserve, and we'll reserve space for an array that's twice the size as the current array. Once we reach this point, we either have space in the array or we've allocated a new array where there's space, and so now we can simply insert the value into our vector and increment num items. If we insert something in the middle of the array, the values at that insertion point are shifted over to make room, beginning at the end of the array and proceeding in the indicated order. We need to start at the last item and move it down one location, and then we can continue on with available space and move one at a time. So we start at the end, move things one at a time in order to create space so we can add the new item at this blue location. Here's the code for our insert method. It takes an index and an item. It does bounds checking, makes sure that there's space, moves items down to make space to do the insert, and then finally inserts the new item. The erase function is sort of the opposite of the insert. We remove the item, and then starting immediately after the item, one by one, we have to adjust each item to remove that blank space. Here's the C++ to do the erase method. So we erase an item at a given index. We check to make sure it's in range. Then we have a for loop where we go ahead and take an item at location I and move it to location I-1. So at the first statement we do this, we'll overwrite the value that we're trying to erase, and then we'll decrement num items when we're finished. So the result of erase is that we'll have a vector with one fewer item. Here's the reserve function that creates a new array that's twice the size of the current array and then copies the contents into the new array. So reserve takes a parameter, new capacity, and if the new capacity is greater than the current capacity, then we'll check to see if new capacity is more than 2 times the current capacity. If it's more than 2 times, then we'll go ahead and make that the current capacity. Otherwise, we'll go ahead and double the capacity. So at a minimum, we're going to double the capacity. Then we'll allocate a new array using our C++ new operator. We'll copy data from the old array to the new array. We free the memory that was occupied by this old array, and we point the data to this new array. So the reason for freeing this data is to prevent memory leaks. And by doubling it each time, it sort of spreads out the cost of copying this data. So our array starts out a certain size, and by doubling it, so if we have an array that's going to grow very rapidly and continue to grow, by doubling it each time, the array we reduce the frequency of this copying operation. Doubling an array size of n allows us to add n more items before we need to copy another array. So we can add n items after we've copied over n existing items. So even though each reallocation is an order n operation, we have to do it only after n items are added. So in terms of how expensive our add operation is, it averages out to about 1 copy per add. So we'll say reallocation is effectively an order 1 operation. So because this insertion is performed in amortized constant time. So in practice what happens is, occasionally there will be a pause while we copy over n items, but that won't happen every time we add. That'll just happen at every n adds. Now the functions operator and at are each a few lines of code and contain no loops, so these functions execute in order 1 time. So if we insert or remove from the middle of a vector, at most n items have to be shifted, so that's order n. So what if we have to reallocate before we can insert? Because we spread out the cost of copying so that it's effectively an order 1 operation, so insertion is still order n. So even if we don't spread out the cost of copying, the copy operation is still order n, so the worst case merely doubles the cost. That's the end of this slidecast.